In this video, we are going to talk about voltaic cells, which are also known as batteries. So this is a very basic drawing of a battery. They don't really look like this. I can explain more in class as far as what batteries look like. We know them as the little round cylinders or maybe the little squares with the two prongs, but what's going on the inside is some version of this, no matter what the shape of the battery. They all pretty much work the same. The parts maybe have a different shape or a different look, but it's all pretty much the same stuff. So batteries are composed of two electrodes. So this is an electrode over here, and this is the electrode over here. And they are just pieces of metal. It could be a chunk of metal. It could be a sheet of metal. It doesn't really matter. It could be a coin for all that matters. Like a penny could be the electrode, or a quarter, or something like that. All right. This would be just a voltmeter. It doesn't necessarily, this would be just if you were measuring like how much power your battery gives out, but this would also be where your electronic device goes. So this would be the thing that you're powering. Okay. We have this thing in the middle that is actually called the salt bridge. I'll explain what that does in a second. And then we have two half cells, half cell 1 and half cell 2, and they are typically filled with a solution. So I'll draw my little bit of a water line there. That's the solution. Okay, and so they're filled with water and some salt. All right, so now let's start figuring out how batteries work. There are some steps down here. So step 1 is that the electrons flow through the wire. This is our wire. They flow through the wire, and they flow on table J from high to low. So if we look at the two metals, Ag and Sn, and we go to table J, we say, all right, which one is higher? Sn is higher than Ag, so the electrons are going to flow from Sn to Ag. That means that in this example, they are going to flow to the right. Now, they don't always flow to the right. I could take these two electrodes and flip them, and then they'd flow to the left. So don't just assume it's one direction. It's always from high to low on table J. Now, there's another saying. They also flow from anode to cathode, okay? So they flow from anode to cathode. So that means that Sn, the name of the Sn electrode is the anode, and the name of the Ag electrode is called the cathode. Next, they also, we have our Leo and Ger, Leo goes Ger, we know that saying, lose electrons, oxidation, gain electrons, reduction. So now think about this. Since the electrons are flowing from Sn to Ag, they are leaving Sn, and they are going to Ag. Ag is going to be where your gain electrons reduction happens, and your Sn is where your lose electrons oxidation is going to be happening. We have another saying at the very bottom, and it's that Leo the lion goes Ger, we know that. And then there's another one, the anox and the red cat. Here's what it means. The anode, that's the an and anox, is where oxidation happens. So anode, oxidation. So as soon as I named this the anode, I actually already knew that this is where oxidation happens. And therefore, the cathode is where reduction happens. So you could have figured it out using Leo goes Ger, but we're also going to throw in the anox and the red cat. Now, the next part of the saying, the anorexic ox gets thin, okay, pardon the phrase, but it works for this example. And then the red cat gets fat, okay? And I'll explain what they mean when we actually get to that part. So the first thing we need to know is that the electrons flow from Sn to Ag, from anode to cathode, and that's where the anox and the red cat are. Okay, so that's how you know those. And then the next part of the saying is the anorexic ox gets thin and the red cat gets fat. And what that refers to is the mass of the electrodes. So the AG electrode is going to get fat. It's going to gain mass. We'll explain how in a minute. And the SN electrode is going to lose mass. It's going to get thin or skinny or whatever you say. Okay, so next part. In the half cells, here are the two salts that are in the half cells. Now, I said the half cells have water in them, but I said specifically a solution. What makes it a solution is it has a salt dissolved in it. So when you take SnCl2, that's a salt, and you put it in water, it is going to dissolve and dissociate into Sn plus 2 with an AQ sign and 2 Cl minuses, also with an AQ sign. AgCl, when it goes into water, it breaks up into Ag plus 1, aqueous. We've done this a bunch of times. You should know how to do it. Now, here's where the saying comes in, which one gets fat and which one gets skinny. The electrodes, when they are in their bar, so these are bars of metal, that means they are in the elemental form. Their oxidation states are 0 because all elements have an oxidation state of 0. These guys are in compounds. Now, granted, the compound broke up, but that doesn't matter. They still are in compounds, or they were in compounds. That's why they have the oxidation states. So look at what happens. If Sn, 0, is the source of the electrons, think about this. If Sn loses an electron, what's its charge going to be? Well, it's going to go positive. In this case, the Sn loses 2, but that's not what's important. Take a look. This Sn, when it loses the electron, it becomes that Sn. So now think about this. If the Sns are losing electrons, they're becoming positive, they're dissolving into the water, what's going to happen to this electrode over time? Well, it's going to dissolve into the water and it's going to get really skinny, like if you were to take like an icicle as it's melting. It's going to get thinner and thinner and thinner. Eventually, it'll totally disappear. I just draw it like that to show that it's getting skinny. And that is where the saying, the anorexic ox gets thin or loses weight or mass, whatever you want to say. Now, those electrons go over here and they actually build up on this electrode. So now I've got these little negatives on this electrode. Now think about this for a second. I've got Ag plus in the water, and I've got negative electrons on the electrode. What do opposite charges do when they get next to each other? They attract. So the Ag pluses from this water or solution are going to actually go to the bar or the electrode, gain the electron, and end up becoming that electrode or that element, Ag0. So that's why this one over time, now think about it. If this electrode over time consistently has Ag atoms or Ag ions getting stuck to it and becoming Ag atoms, remember the atom and ion word mean different things, this electrode is going to gain mass over time. So it's actually going to get bigger and bigger and bigger. And it'll look something like that. Think of it like, I don't know, if you've ever made a candle, if you ever like gone to one of those like old-timey places where they have you dip the candle in the wax, and every time you dip the candle in the wax or the candle string, it gets a little fatter and a little fatter and a little fatter, and eventually it makes a bigger candle. Well, that's basically what's happening here. All right, so that's where the two sayings come from. The red cat gets fat, the anorexic ox gets thin. That will always be true, okay? Whichever one is the anode is always going to lose mass. Whichever one is the cathode is going to gain mass. Now, if this was all that your battery had, nothing would happen, right? Because this would happen once or twice, and then your battery would lose power and it wouldn't actually work. Here is where the salt bridge comes in. The salt bridge prevents ion buildup. Now think about this for a second. If the SNs are becoming positive and jumping into the solution, what's going to happen to the amount of positives in this solution over time? Well, it's going to become more and more positive. Do two positives want to be next to each other? Well, of course not. So if the two, eventually what would happen is this solution would build up with positive charge, and then your SN atoms aren't going to want to go into your solution to become SN ions because they don't want to be more positives next to each other, and that would stop your battery from working. The same thing over here, where you were using up all the positives from the solution and making them stick to the battery. That's making the solution become more negative because that's what's left behind. Eventually, if the solution becomes too negative, then the ions aren't going to be attracted to the electrons anymore because the solution that they're in will be more negatively charged than the electrode itself. That will make your battery stop working. So what do? We allow the excess charge to go through the salt bridge. In other words, your SN ions here are going to travel through. This salt bridge is filled with solution or water or whatever, and the Cl minuses are going to go through here to attract. And basically, you get a buildup of positives here, you get a buildup of negatives here. The salt bridge allows them to come together and cancel out the buildup, which makes your battery keep functioning. So when we think of the salt bridge, here's what it does. It's called ion migration, or the words mean the same thing as far as we're concerned. It allows ions to go from one side of the other, which is what a bridge does. If you think about it, bridges allow people or cars to go from one side of land to another, crossing a body of water, right? And this is a bridge specifically for salt. And another word for salts when they dissolve in water is ions, hence the term salt bridge. It prevents charge buildup in the battery, okay? So that's what salt bridges do. Last but not least, we have to draw the two half reactions for this battery and we're done. But here's the good part. We actually already did it, or we did 2/3 of it. See how SN0 became this SN2 plus? Well, guess what? That is your oxidation half reaction. Take a look. SN0 turned into SN plus 2. Now that's most of it. We just need to figure out, well, we know it lost electrons because it's oxidation. So going from 0 to plus 2 means you lose 2 electrons. So I add 2 electrons to the right side. There's my half reaction. If you wanted to get fancy, you could add in the symbols. This one was a Q and this one was a bar, so it was a solid, but it's not really necessary. And then the other half reaction, well, guess what? We have it over here. We've got the Ag0 became the Ag plus 2. We already drew it out. So, or plus 1, sorry. Ag plus 1 electron becomes Ag0. That was the solid. That was dissolved in water. And there's our two half reactions. To balance them, we would just use multipliers. That one gets multiplied by 2. And this one could be left alone or have a 1 put in front of it. That's a total balance problem. These were the steps I took to do it. This is the important information that you need to know. Batteries convert chemical energy to electrical energy. When they run out of chemicals, they run out of electricity. That's why batteries go dead. Basically the anode and the cathode the anode gets fully used up, and then once there's no more anode, then the cathode can't gain mass anymore, and the electrons can't keep flowing, and so your battery dies. Rechargeable batteries actually reverse the charges on the anode and cathode and force this reaction to go backwards. This is where spontaneous and non-spontaneous comes in. That when the battery's operating as normal, we call it spontaneous. When you recharge a battery, if it is rechargeable, that would be the non-spontaneous reaction because you're forcing it to go backwards to recharge your battery. So that concludes this lesson on batteries. Voltaic cells, think of an easy way to remember voltaic cells. What are they? Batteries are rated in volts, like a 9-volt battery is that square one. So when you think voltaic, think batteries. That's an easy way to remember it. That's batteries in terms of the notes. We will be doing a couple more versions of this. We'll do electrolytic cells and a couple other things after this. But that concludes this video. In this video, we are going to talk about electrolytic cells, also electroplating. They're basically the same thing. There's different versions or different types of electrolytic cells. Electroplating will be this video. I'll discuss the next two in the next video. But basically, this is where gold-plated jewelry comes from, or silver-plated jewelry, or if you wanted a chrome-plated, like a car part, like cars that have lots of chrome on them, or motorcycles. Those are not solid chrome pieces. Those are metal or steel or iron, and then they are typically chrome plated because the chrome looks nice, but the chrome isn't very strong, and so you need an iron core or a steel core in order to make the wheel strong enough to be usable, but then you want the chrome on the outside to make it pretty looking and shiny. So that's where all this comes from. Now, we use a lot of our battery terminology here. We are going to have an anode and a cathode and things like that. But before we get to that, think about what's happening. We want to take silver and we want to put it on, this is my version of a vork, like if you had silverware that was silver plated. I know it's a terrible drawing, but this could be a car rim, or it could be a piece of jewelry, or it could be anything that you want to put a coating of metal on top of. This is going to be your red cat. It's going to gain mass. Basically what we're going to do is we are going to put a thin little layer of gold or silver or platinum or whatever you want to put on it. We're going to put a thin little layer over all the parts in order to make this our, metal plated jewelry. Therefore, it's always going to be the red cat. This one is always going to be then the anox. Another name for these anodes are actually called sacrificial anodes, because essentially we're taking the metal here and sacrificing it to go to there, okay? And that's pretty much it. So we actually answered most questions. We know this is where reduction is going to happen. This is the name of this is the cathode. It's going to gain mass. This is the anode. It's where you're going to lose mass. It's where oxidation occurs. Now let's look at how it happens. So you put these things in a solution. So we have a solution of salt, just like in a battery. The salt solution, it has to be the salt. The salt has to contain the metal that we want to plate. So in this case, we want to plate silver. So I use a silver salt. When I put it in water, it's going to break up into Ag plus 1 AQ and Cl minus 1 AQ. We don't care about that part. And now let's plate it. So think about this. We want to get the silver ions to the fork. So the silver's positive. Notice the fork is connected to the negative part of the battery. And the reason, we put the negative over here, so that way the silver gets attracted, gains an electron, and becomes Ag0, that's solid silver, on the surface. So we need that to happen. Now, what would happen initially is we would just use up all the silver ions that are in the water very quickly, and we wouldn't have enough. So the way we do it is we replace the silver ions with the silver electrode. Every time the ion leaves the water, you're going to get new ions that are coming out of the bar and coming back into the water to replace them. So the Ag0 over here, this is solid silver again, and over here it's also solid silver. The zeros are always the solid. It's going to be dissolved over time, and the bar eventually will totally disappear, and it'll create silver ions. Guess what? Once you understood that, we're done. If you look at it, we have our two half reactions. Take a look. The oxidation half reaction is the one where it's losing electrons. Well, this silver became this silver by losing electrons, and the reduction is gaining the electrons. Well, this silver, I'm going to try to like half highlight them to show you that it's actually the same thing, went over here and became that one. So for reduction, let's do oxidation first. We have Ag0, that's this one. It's going to turn into Ag plus 1 plus an electron. That's this. That electron went through the wire to go over to the fork. Then the reduction happens, and we have Ag plus 1 gains an electron. In theory, it gained the same electron that this one gave up, but not really. But so it gains an electron, and it becomes Ag0. These zeros are the solids, and the charged ones are dissolved in water. There's my two half reactions, and with this type of reaction, they're always going to be balanced, but I'll do it anyway. They're both ones, but you really don't have to worry about it here. It requires a DC power source, that's a battery. It has, if you notice, there's no half cells, there's no salt bridge, there's no need because everything's in one large container. The salt bridge is to prevent charge buildup, but since everything's happening in here, there wouldn't be any buildup anyway. There's no half cells, it's one giant cell. the charges on the anode and cathode are actually reversed. So normally, the cathodes are, in a battery, the cathode is positive, the anode is negative, because cathodes make cations and anodes make anions, words we should know, okay? But since we're using a battery, this is only in a battery circumstance. In this case, we're using a battery to power something else that's not a battery. The charges get flipped. And then the last part, electrolytic cells. They use electrical energy to make chemical reactions happen. So they convert electrical to chemical. This would also be what you would need to do to recharge a battery to make it go backwards. But this is one version of an electrolytic cell. There are two others that I'm going to talk about in the next video. They're also very short like this. This video is going to be on electrolysis of water and salt. It is very similar to the electrolysis of, or electroplating electrolysis, except neither one of them is going to be the definitive red cat, I guess you could say. So we'll get right to it and I'll explain how it works. So electrolysis of water, if you think about the word electrolysis, it really is broken up into two, electro and lyse. Electro means electricity, and lyse talks about, like, think of it like lysosomes in cell biology. They're what split the cell in half. And so it's really using electricity to split up water. That's basically what it means. And so we take a water molecule. So we have this whole thing is submerged in water. And when you apply a direct electric current, so a DC current to it, water has a tendency to split into two H pluses, because there's two of them, and one O minus 2. So it splits up into those. And then your basic rules of opposites attract apply. The negative attracts to the positive plate, and the positive attracts to the negative plate. So let's look at what happens at the positive plate. At the positive plate, we have an oxygen that's a -2. So it's oxygen with 2 extra electrons. That is going to turn into plain old oxygen, which is 0. And it does that by giving up the 2 electrons that it has. And then the reverse happens, and that's why it's oxidation, because it's losing the electrons. And then the reverse happens here. We have H plus 1. It gains an electron and turns into H0. And then those are your two half reactions for this. They're very, very easy. Now, I have, before I've said that, well, these can be balanced as well. I said that the half reactions that we learn are essentially oversimplified. The real half reaction, we know that oxygen is diatomic. It's part of Brinkelhoff, as is H. And so these things don't really exist like this. What's really happening is 2 oxygen -2s are turning into an O2, which is the diatomic form of oxygen, and it's doing that by losing 4 electrons. And then here we have 2 H positive ones, and they're going to gain 2 electrons, and they're going to turn into H2. So those are the true reactions. And again, the balancing coefficients would actually still be the same. We would still need to essentially do this 2 and 1 in order to balance these, because there's twice as many. But that's pretty much it for electrolysis of water. Where would we use this? Well, this is actually used all the time when you want to make oxygen. For example, a common application of this is on the space station. When you're in outer space, you can't bring up just tanks and tanks and tanks of compressed air. They're too heavy. So what do you bring up? Well, you bring up some water, and then the water can be split into hydrogen and oxygen. You can use the hydrogen to do things with it, like generate power and things like that, and then you can breathe the oxygen that comes off of it. So this is a process that it just uses simple electricity and usually some catalyst like an acid, like citric acid or things like that. But it's used all the time for practical applications for generating oxygen and hydrogen, for that matter, if you needed hydrogen for something. And then the next application is electrolysis of salt. Same idea, except now we're going to use a salt. So when we use a salt, like for example, I'm going to use KCl, but we could use table salt. It doesn't matter. Now, with electrolysis of salt, there's one issue. The salt has to be in the liquid phase, and that typically requires very, very high temperatures to get liquefied salt. But it is possible, and it can be done, and it is done all the time. And now that salt, when you put it in the electric current, it will actually break the molecule or the compound up into K+, which is in the liquid phase, and Cl-1, which is in the liquid phase. But again, it's just like electrolysis of water. The positive goes to the negative goes to the positive, and then you have oxidation and reduction. So chlorine liquid is going to turn into Cl0, which is a gas when it's in the elemental form, by losing an electron. And again, this is not the real reaction. I'll show you the real one in a second. And then here we have potassium, which is +1. It's going to gain an electron by going to this. It's going to the negative. It's negative because it has electrons on it. That's why it gains the electron when it gets there. And it's going to turn into K0, which would be a solid or a liquid depending on the temperature. It doesn't really, honestly, that's not that important. And that's what it looks like. Now in real life, there's one caveat. The chlorine is a naturally diatomic, so you really have 2 chlorine -1 liquids that turn into a Cl2, which is still a gas, and 0. And it's going to gain or lose 2 electrons by doing this. And then the potassium doesn't change. And so then balancing these would really be 2 and 1. If you were just doing these 2 reactions, then they would be 1 and 1. So just be aware of that. What is this used for? Well, it's used to purify elements that you can't find in nature pure, either at all or very often. So like, for example, group 1 and group 2 elements, the alkaline and the alkaline earth, they are so reactive that they will catch on fire if they touch water. So if you think about that, there's no place on the planet where elements can get away from water completely. Even in the most dry desert on Earth, those deserts have only been deserts for maybe 10,000, 20,000 years or something like that. At one point there was water present, and even in the desert it does rain from time to time. So these elements are never found anywhere in nature pure. They're always found in compounds. Well, if we needed them pure for something, then this is the only way to really purify them. Now, group 1 and group 2 are obvious because they are never found in nature pure. Other elements are found in nature pure, but in very low quantities, and so it's easier to just purify them through this process from compounds. Like, for example, aluminum is almost never found in nature pure, same with copper and things like that. So if you had compounds that contain them and you needed to purify the metal out, this is how you would do it. The salts must be in the liquid form in order to do that. And so that is our video on electrolysis of both salts and water. They work off the same premise. They are slightly different from electrolysis or electroplating, but the concept or the application is pretty much the same.